Section 7. The deep circulation of the ocean. Digging deeper. Ocean currents. Seawater temperature, salinity, and density. In the Investigate, you ran models that showed how water moves in the oceans. You saw that it can sink, rise, or flow horizontally. The movement of deep ocean water is controlled by the density of the water. As you found out in the Investigate, the density of seawater is determined by two factors. These two factors are temperature and salinity. Both are important. However, temperature has a much greater effect than salinity on seawater density. The sun heats Earth's surface unequally. This is because the sun's rays strike Earth from nearly overhead at low latitudes, but at a very low angle at high latitudes. In winter, the sun does not shine at all north of the Arctic Circle and south of the Antarctic Circle. The warm surface water at low latitudes stays at the surface because it is less dense than the deeper water. Surface seawater that is chilled at high latitudes, especially in winter, increases in density. When a mass of water is more dense than surrounding water, it sinks under the pull of gravity. You observe this in the Investigate with the sinking of the cold water. Ocean water contains dissolved salts. The concentration of dissolved salts in seawater is called salinity. It is expressed as parts per thousand. The salinity of ocean water is approximately 35 parts per thousand, meaning 35 grams of salt per 1,000 grams of ocean water. The higher the salinity of ocean water, the more dense the water is. When the salinity of a mass of water is increased, the water sinks relative to surrounding masses of water. In some areas of the ocean, evaporation from the ocean surface is greater than precipitation onto it. This increases the salinity. As a result, the water tends to sink. In other areas of the ocean, precipitation is greater than evaporation. This decreases the salinity. The water stays at the surface. The salinity of ocean water is also lowered where fresh river water flows into the ocean. At high latitudes, the temperature of the air above the ocean is far below freezing. Seawater freezes to form sea ice. This removes fresh water from the ocean. As a result, the concentration of salt in the water left behind increases. Because ocean water at high latitudes is also very cold, it is the densest water in the world's oceans. Water masses. The ocean is a single body of water. However, it is not the same everywhere. Both the temperature and the salinity of ocean water vary from place to place. Large regions of the oceans have water with about the same temperature and salinity. Such a region is called a water mass. Oceanographers are scientists who study Earth's oceans. They define water masses mainly by two factors. These factors are temperature and salinity. In the surface layer of the ocean, winds mix the water vertically. This happens down to depths of 100 to 200 meters. This mixing causes the temperature and salinity to be about the same throughout the layer. However, in most areas of the deep ocean, there is no vertical mixing. Therefore, individual water masses keep their distinctive properties for a long time. Water masses are named for where they form. Antarctic bottom water and North Atlantic deep water are two examples. Antarctic bottom water is formed in the southern hemisphere near Antarctica. It is formed by cooling of the near-surface water. It also has increase in salinity due to formation of freshwater ice. The water then sinks. It flows north away from Antarctica for thousands of kilometers along the ocean floor. It flows all the way to the high northern latitudes. Both North Atlantic deep water and Antarctic bottom water play an important role in the circulation of the world's oceans. North Atlantic deep water forms in the region around Iceland. It has an average salinity of 34.9 parts per thousand. Its temperature is about 3 degrees Celsius. It takes as long as 1,000 years for a parcel of North Atlantic deep water to sink, move south, circulate around Antarctica, and then move northward to the Indian or Pacific Oceans. Antarctic bottom water is the most dense of all deep ocean water masses. It has a salinity of 34.7 parts per thousand. Its temperature is negative 0.5 degrees Celsius. It forms at the edge of the Antarctic continent. Also, it flows under all other water masses as it moves northward along the deepest part of the ocean bottom. What causes the deep circulation? The slow movements of the deep water masses form a gigantic and complex circulation cell. The cold waters that form near the surface at high northern and southern latitudes flow toward the equator. The deep waters gradually rise up toward the surface at low latitudes, where they are warmed and flow back to high latitudes to complete the loop. Oceanographers are not certain about the overall flow rate of this circulation. It might be as high as 20 million cubic meters per second. That is 100 times the flow rate of the Amazon River, the largest river on Earth by flow rate. One cycle on this conveyor belt takes between 500 and 2,000 years. Oceans are heated at the surface at low latitudes and cooled at the surface at high latitudes. It might seem natural to you that they form a huge convection cell. However, you saw in Part C of the Investigate that a tank of water that is heated from the top at one end and cooled from the top at the other end does not form an active convection cell. Oceanographers have known for a long time that another explanation is needed to account for the deep circulation of the oceans. What is needed is a way to mix the cold water in the deep ocean at low latitudes with the warmer water that lies above. Then, because warm water is less dense than cold water, the mixed water rises toward the surface to complete the circulation cell. The problem is that oceanographers are still not sure what causes the mixing. One idea that is becoming widely accepted is that the tides cause the mixing. The tides cause movement of water not just in the shallow coastal oceans. They also cause movement everywhere in the oceans, including the deep ocean. Does it seem strange to you that the deep circulation of the ocean might be caused by the moon? The geosphere beneath the oceans. The ocean is mostly very deep. The average deep ocean depth is 4 or 5 kilometers. The bottom of the deep ocean is a place of inky blackness, eternal cold, and water pressures that are unimaginably high. In another sense, even the deep ocean is shallow relative to the surface area covered by the oceans. Suppose that an ocean such as the Atlantic or Pacific were the size of a football or soccer field. You would be wading around in an ocean that is no deeper than your ankles. Earth's ocean basins contain various landforms. Closest to any continent is the continental shelf. This is a wide area that begins at the very shoreline and slopes gently toward the open ocean. Continental shelves vary in size, extending offshore for a few tens of meters to over 1,000 kilometers. They are the shallowest parts of the ocean. Generally, they do not reach depths of more than 100 meters. The rocks of the shelf are usually covered with young sediment that has been carried from the continents into the ocean basins by rivers and streams. Near the shore, where the bottom is shallow and affected by waves, the sediment is typically coarse and sandy. Farther offshore, in deeper and quieter parts of the shelves, The sediment is fine-grained mud. At the edge of the shelf, the continent slopes downward more steeply. This is called the continental slope. Most slopes are covered by mud and silt that have been carried across the shelf and over its edge to rest on continental rocks. The steepness of the slope causes these sediments to build up only for a short time. They eventually become unstable and slide downward to the base of the slope. This is similar to the mass movement on Earth's surface, however, it takes place underwater. Beneath the sediments that cover the base of the continental slope, continental crust meets oceanic crust. The continental rise is made of thick piles of sediment that lie at the base of the continental slope. The rises are mainly mud, silt, and sandy sediments that have been carried down the slope from the continental shelf before finally coming to a rest on the oceanic crust. Together, the continental shelf, slope, and rise are known as the continental margin. Beyond the continental slope lies the abyssal plain. This is the surface of the layer of sediment that covers oceanic crust. Generally, this is what is thought of as the deep ocean. On average, it is between 4 and 5 kilometers below the ocean surface. The plains are extensive features. Their flatness reflects the blanket of sediments that can reach up to 5 kilometers thick. Abyssal hills can rise 900 meters above the plains. Most hills are protruding rock formations covered with fine sediment that builds up slowly over the whole ocean floor. The abyssal plains and their hills cover more than 3/4 of the ocean floor, or half of Earth's surface. Oceanic trenches are long, narrow, steep-sided troughs. They are the deepest parts of the ocean. They can form where denser oceanic crust at the edge of the ocean floor meets less dense continental crust. Here, oceanic crust bends downward, forming the trenches. These can reach great depths, often several kilometers. The deepest is the Mariana Trench in the Pacific Ocean, around 11,000 meters. Oceanic trenches can also form where the two pieces of oceanic crust meet. Much like when oceanic crust and continental crust meet, one of the pieces of oceanic crust bends downward, forming the trench. The warm ocean and the cold ocean. The ocean is layered by temperature. There is an upper layer of warm water and a much thicker, deep layer of cold water. At low latitudes, the change between these two layers is at a depth of a few hundred meters. Above that depth, the oceans are as warm as 25 degrees Celsius over large areas at low latitudes. Below that depth, the ocean is much colder. In the lowest parts of the ocean, the temperature is not much more than 0 degrees Celsius, even at the equator. Between about 200 meters and 1,000 meters below the surface, the temperature of the water decreases sharply with depth. This is a zone of rapid change from the warm to cold water with increasing depth. It is called the thermocline. You may have felt a difference in temperature when treading water in a lake. Water around the upper part of your body may have felt warm. At the same time, the water near your feet felt colder. The thermocline is a larger scale version of this. Cold water is more dense than warm water. Therefore, this transition zone is called the pycnocline. The reason that the pycnocline is also the thermocline is that the density of seawater depends mainly on the temperature of the water. The circulation of the oceans. The warm, shallow part of the ocean is in a state of continuous movement of circulation. This part is above the thermocline. The cold, deep part of the ocean is also in a state of continuous circulation. The nature of these two circulations is very different. Oceanographers have been describing the circulation of the ocean for over 100 years. At the same time, they have also been trying to develop theories to account for it. It is a very complicated problem, and there is still much to be learned. It is a major area of research in oceanography.